Welcome to SJCE content. I am Dr. D.Shoba, Assistant Professor, Department of Physics, St.Joseph College of Arts and Science, Autonomous Cuddalore. In this video, I am going to teach about different types of electric polarization take place in dielectric materials. We have 4 types of polarization mechanism. That is electronic polarization, ionic polarization, orientation polarization, space charge polarization. These polarization occur due to the microscopic mechanism. In DC field, the macroscopic polarization P vector is created by these 4 polarization mechanisms. First, we will see the electronic polarization. The electronic polarization is due to the displacement of positively charged nucleus and negatively charged electron of an atom in opposite direction on the application of external electric field. This results in the creation of dipole moment in the material. The dipole moment mu is proportional to electric field strength E. Here alpha E is the electronic polarizability. Let us see the calculation of electronic polarizability alpha E. Consider an atom of dielectric. Of nuclear charge Ze, where Z is the atomic number. The electron of charge minus Ze are distributed uniformly throughout the sphere of the radius R. The center of the electron cloud and the center of the nucleus are at the same point, hence there is no dipole moment. The charge density of the charged sphere is given by total negative charge divided by volume of the atom. The charge density is represented by a letter rho, which is equal to the total negative charges minus Ze divided by volume of the atom 4 by 3 pi r cube. And rearranging, the charge density rho equal to minus 3 times Ze divided by 4 pi r cube. With DC electric field, when this atom of dielectric is placed in a DC electric field of strength E, 2 phenomena will occur. One is Lorentz force acting on the atom and the Coulomb force. Number 2, Coulomb force acting on the atom. Due to the electric field, the electron cloud and positive nucleus experiences a force called Lorentz force in opposite direction. Due to Lorentz force, the nucleus moves towards the field direction and electron cloud moves towards the opposite direction of the field. In this figure, we see that the center of nucleus is separated from the center of the electron cloud. We have the small distance of separation x. Due to this, we will get the dipole here. The Coulomb force, when the nucleus and electron cloud are shifted from their equilibrium position, an attractive Coulomb force is created. It will tend to maintain the original equilibrium position. Finally, a new equilibrium position will be reached when these 2 forces are equal and opposite. Now there is a distance x between the center of nucleus and electron cloud. Now see the Lorentz force between the nucleus and the electron, which is equal to charge into electric field. Then one of the charge we are taking the nucleus charge is Ze and the electric field is E. Name it as equation number 2. Coulomb force between the nucleus and electron is given by the relation 1 by 4 pi epsilon naught Qp and Qe. Qp is the charge of the nucleus, Q is the charge of electron cloud, and they are separated by a small distance x. The charge of nucleus is we are taking ZT, and the charge of the total electron in the sphere of radius x, we are going to calculate total negative charge enclosed in the sphere of radius x. It will be calculated using the relation charge density into volume of the sphere of radius x. So after substituting the values, we are getting the Coulomb force is equal to minus z square E square and x divided by 4 pi epsilon naught r cube. At equilibrium, the Coulomb force and Lorentz force must be equal and opposite direction. Therefore, FL equal to minus FC. FL represents the Lorentz force, FC represents the Coulomb force. On equating these two forces, we are getting the distance of separation between the electron cloud and the nucleus, which is equal to 4 pi epsilon naught r cube E divided by ZE. Due to shifting of electron cloud, the atom gain some dipole moment. That dipole moment is equal to magnitude of the charge into distance separated by the dipoles. Here the magnitude of charge is ZT, distance of separation is x. Now we are going to substitute the value of x here. We get the dipole moment mu equal to ZE into 4 pi epsilon naught r cube E divided by ZE. And cancelling these two ZE, we are getting 4 pi epsilon naught r cube into E. Name it as equation number A. But dipole moment in terms of polarizability, we can write mu equal to alpha E into capital E. This is an applied electric field. Alpha suffix E represents the electronic polarizability. And comparing these two equations A and B, we are getting the electronic polarizability E equal to 4 pi epsilon naught r cube. The electronic polarizability is independent of temperature. There is no temperature term involved in the above equation, and it is proportional to the volume of the material, that is volume of atom in the material. This kind of polarization occur in all materials. Thank you.